Thank you, Jenny. Sounds good. Yeah, I think so. Hello, my name is Sergio, and I will be just talking about with you about the development of in-lake predictive tools for suspended sediment and mercury dynamics. Louder. Hello, hello, hello. That was not me. Is that better? Oh, okay. So again, thank you, Janine. Thank you, Angela, for all the organization and everyone that has been involved. For everyone that didn't hear me, my name is Sergio Valbuena, and here I'm just presenting the rest of the co-authors of this work, and I will be talking about the development of predictive tools in the lake for sediment, suspended sediments and mercury dynamics. All right. I think this will be better. So a little bit of what we're gonna go through. I'm gonna be talking about what is entails about the numerical, like developing a numerical model, and what is the process that entail, and then I'm just gonna go through different steps that we go through. I will be talking about the conceptualization of these numerical models. Then I'm gonna give some examples. First, for the suspended sediment model that we developed. And I will split that into the implementation, test, and validation. And then I'll do the same with the mercury transport and transportation, which is a continuous work that we're doing right now. What is a numerical model? A numerical model is basically a mathematical representation of natural systems in which we try to represent mechanisms to predict or understand different physical and biogeochemical processes in natural ecosystems. So we try to understand complex systems, and developing a numerical model goes through different steps, all of them being represented in circles in here because they are really cyclic. We might need to go back and forth to understand and to be able to capture properly and edit the different steps that we go through. So the conceptualization per se is where we define the physical and biochemical processes, the different mechanisms, how they interact between each other, and that basically the output from this is a conceptual map where we describe this connectivity. We move into the implementation where we basically use the conceptual map that we develop, and we start transforming this into mathematical expressions. We start analyzing the assumptions that we need to make in order to be able to implement this into a computer and through be able to use numerical methods to solve these equations and obtain a model that is capable of receiving some type of inputs and just give us results and in the form of outputs that predict the behavior of our natural systems. Then once that's done, which actually no one sees, we start showing the test where we analyze single processes and we start analyzing the inner process interactions of single mechanisms. This is just simplifying different systems in a better way. You will see examples in the next slides. But just to make sure that our model is working properly and that we'll be able to predict the results or like to predict the conditions in the real systems, in particularly in this case, Clear Lake. Finally, once we're satisfied with the test of these simple systems, we move into the validation step where we can be analytical from laboratory experiments, but also field observations or in situ observations. And we basically use what Charlie has been collecting and many other researchers have been collecting data in the lake and compare the numerical results with this, and the error between those between that data and the numerical results is a statistical metric that we use to calibrate and make better our numerical model. So I'll start with the suspended sediment conceptual model that was developed at Turk. I did this as a previous step for the mercury model, and we needed to implement this to be able to characterize the mercury better in Clear Lake. As Karen mentioned and Charlie mentioned, the mercury can attach to the sediments. Therefore, we need to represent sediments correctly in the lake. Here what we're looking at is just the conceptual model itself, where we have the water in blue and the sediment in yellow, brownish. And the errors are just describing the different forces that are irrelevant to this model. So we have diffusion advections. That just simply means how we interpret the water motions vertically and horizontally in our domain. Then we have the gravity, because it's sediment, the sediment is heavier than water, and it will tend to fall to the lake bed. And then we have erosion and deposition. That basically tell us the mechanisms that are capable of getting sediment from the lake bed into the water column. And then the deposition is the mechanisms that brings the sediment from the water column and just settles down to the sediment to the sediment layer. Once again, this is just simple. We don't need to understand the complicated equations there, but it's just to give you an example of what actually goes into computer to be able to represent the mechanisms properly. Here I'm just showing again the arrows for the erosion and deposition. What needs to be known, sorry, what needs to be known in here is that the balance between the resuspension and deposition will definitely give us a knowledge if sediment is being lifted up from the bed into the water column. And both deposition and erosion, same as the setting velocity of the particles, are dependent on the sediment size and sediment density. And then if we have any sort of erosion, it will be because the water currents at the bottom of the lake are sufficient to pick up that sediment into the water column. So now we move, so this is just the mathematical representations, part of the implementation. And if we move into the test, like I say, there are simple cases, simple scenarios, and in this case we have a hypothetical case where we are looking here. In the vertical is just the depth, and in the horizontal axis is just distance. So if we're looking in this way, we're looking at a pool from the side, and where we're looking at the light blue with high concentration of sediment. So we have a pool that has significant amount of sediment, and then the right panel is just showing in a line what we'll see the average concentration of this whole section. So a way to see it is just we have a pool with sediment. So what happens if there is no any water movement? What happens with the sediment? And this is just the result of it. So as we can see, because the sediment has a gravity, it will start falling down to the bottom all the way to the layer, sediment layer. It's worth noting that in here I'm just representing the water column. Let me see if I can read. I'm just representing the water column. I'm not considering the accumulation that we'll see in a real system in the sediment layer. So we can see because there is no water movement, the sediment just settles down until it gets out of our system. So that is just a simple test, and once we are satisfied with this behavior, we move into more complex systems. In this case, is the evaluation of hypothetical scenarios at Clear Lake, because that's our preferred lake. So what we're looking at here is two hypothetical scenarios. And what I want you to understand first, or to focus on, is the difference between the two of them. The one on the left is a clear lake in which there is no wind, meaning the water currents, the water is stagnant, is not moving. And the other side, we have clear lake with wind, with real meteorological conditions from the summer of 2020. What we see in gray line is just this cross section representing the oaks arm. And again, the colors in here is the light blue for high sediment concentration, and the rest of this, the dark blue, is for zero sediment concentration. So this basically just tells us a scenario in which we release sediment at the surface. So what will happen? Basically, on the left, we can consider it as the pool example, and on the right side is just the actual system. So if we look at the results, we can start seeing the difference where we see on the left side, we see because the water is not moving, the sediment is depositing right straight to the bottom. In this case, we actually see the accumulation of sediment at the bottom of the lake. But it will focus on the right side, the actual conditions in our lake. We can see that the water currents start moving the sediment around all the way that is actually depositing all that sediment all across the oaks arm. And this is really important because if we consider any sort of remediation strategies that implies releasing a sediment at the surface, we have to take that into account for the amount of sediment that we want to put in there. And this is just because if we are targeting a specific location, we'll have to account that the sediment is probably not gonna fall in there because of the currents. So now if we move into a little bit, so in the previous was just deposition, right? In this one, what I want to show, yes, you're reproducing, is a Clear Lake sediment resuspension event. Again, these are for the conditions in which Clear Lake experienced during the summer of 2020. This is just a little time window of about 160 hours, but when the assumptions in here is that the lake bed, so we're assuming that our lake initiates with a material that is covering the lake bed of the bottom of the lake. So what happens if we have the winds that we experienced in the summer of 2020? Well, we can see from the videos, and I hope it is, maybe I have to reproduce again. Yeah. What we can see is that during that wind event, we can see that a lot of sediment was picked up from the bottom and lifted up all the way to the surface. And actually, this sediment that was picked up could actually be transported because of the currents all the way to the upper arm or the lower arm. And this is just an example of how complicated or how complex dynamics the currents are in Clear Lake and how we should take that into account again if we want to do or consider remediation strategies that involve these sort of solutions of putting sediment on the bottom. So I talk about the suspended sediment conceptual model. Now I'm talking about the mercury conceptual model, which you have seen less complicated graphs for the conceptual model. But I want us to focus in here is just to see the complexity of all the processes that involve developing a numerical model. And the more errors that we see in here between all these boxes, the boxes are just the mercury species, are just the different processes that we need to account in implementing. And the more errors that we see in a conceptual model like this, the more complex it is to implement, the more complex it is to get it to represent the actual conditions of our lakes. And it's more likely that we'll need more data also to make sure that the model is behaving correctly. Okay, so again, similar to the same conceptual model. Once we have the conceptual model and after we implement that into a computer, I'm not showing the part of the computer because it doesn't make any sense. It's just a test. We start testing with simple cases. In this case, we're looking, again, the top panel is just for elemental mercury, Hg0. The middle panel is for Hg2, and the bottom panel is for methyl mercury. In this simple case, we're analyzing how the concentrations increase because we're putting an inflow on the left side that is going to carry a mercury with a velocity and is going to carry all the way to the right side. So if we play the video, we're going to start seeing how the mercury it gets accumulated in the whole water column, and the bottom is just blue because this is a simple test, and the test didn't include the concentration and the transfer of concentrations from the sediment layer to the water column itself. So we can see as the flow develops, because there is an inflow coming in, we start seeing how the concentrations increases to a point that reaches a constant value. This constant value gives us some validation that the numerical model is predicting correctly. So if we move into a second test, this is again the same. Blue means, sorry, I didn't explain this before and I apologize. Blue is low concentrations and red is high concentrations of mercury. But again, in here we have elemental mercury, Hg2, and methyl mercury at the bottom. But in this case, instead of analyzing an inflow of mercury, what we're going to analyze is the atmospheric deposition of mercury into our system. As we can see from the video, the atmospheric deposition starts being at the surface, which gives us confidence that the numerical model is behaving as we expect, as the atmospheric is just like the top layer, and then it starts accumulating again, remains at the top, but it starts accumulating in like deeper layers. And the difference that we can see from the left to the right is just because there is an inflow of clean water coming from the left, and that's why we create this difference between the two ends of our system. Twice. And just to finalize a little brief of the summary and next steps, I just wanted to recall that we are building on previous numerical models that have been developed at Turk. These are the three main components. it has been developed a hydrodynamic model which has been calibrated or validated. So that gives me a step up because I'm confident that we're reproducing the water movement and the temperature of the lake correctly. It's also including the river flow dynamics, and then there has also been the development of the water quality that includes the nutrients, dissolved oxygen, and phytoplankton, which are important for analyzing mercury in a system. We have developed, and now part of this project, this is a project that is funded by CNRA. The contract was signed at the end of 2023, but the project dates goes from July 23 to June 26. And the status right now is that we have developed the suspended sediment model as, again, like I said, as a pre-step for the actual development of the mercury model. We implemented a sediment layer, which wasn't a part of SI3D at the beginning. And we also implemented just the different mechanisms for representing suspended sediment in the lake. We developed the equations, so we did the conceptual model and we developed and implemented the mercury cycling equations into the model. And we are in the phase that we're initiating the tests for different single mechanisms, and I'm increasing those tests in complexity as we speak. And I have also developed pre and post processing for being able to understand data, to input it into the model, and also understand the results from the numerical model itself. We'll be using USGS data from 2020 to 2023 to calibrate the numerical model. And then for the next steps is to validate and calibrate the numerical model with actual clear lake conditions, because at the end, that's what we care for. We care for this system, and we want to make sure that we're representing it correctly. And then there will be a model that will provide inputs into or insights into the biooptic to a lower food web. This will be a separate model. It's not going to be a part of SI3D, but it will feed up from the results from the model that we are developing. We'll be evaluating mercury dynamics under hypothetical hypolytic oxygenation scenarios. And just because of the timing of the HOS system program that you will hear later on, there is a probability in which, because of the timing of the projects, that this project will need an extension to be able to analyze in conjunction what is happening with the oxygen and what that affects, on how that affects the mercury concentrations in the lake. Thank you so much.